Okay, so welcome everyone for our last meeting this term. Today we are very happy to have Denis Auroux, who is going to tell us about Lagrangian Floer theory and analytic functions on Riemann surfaces. Thank you for joining us today, and please take it away.
All right, so thank you for the introduction. And yeah, again, really sorry I couldn't make it in person, but anyway, life happens. But you know, I'm sure it's only a matter of time. All right, so I'm going to try to tell you about things that are very, very elementary for most of the talk. And then near the end of the talk, they will veer into things that are more conjectural and maybe less correct. But, well, I mean, they're actually theorems, but the question is whether they're philosophically correct. They are mathematically correct. The philosophy is more questionable. And so the punchline of the talk will be recent joint work that I've done with Sasha Efimov and Ludmil Kedzarkov back when it was still Peaceful World. But anyway, 2021, we have a paper on archive. But this is also based on earlier work that I've done with various other people and the thesis of my former student, Heather Lee. Okay, so let me dig right in. So this is going to be a talk about homological mirror symmetry for surfaces or curves, depending on whether you count real or complex dimensions. And so I'm going to start right away by telling you about the wrapped Fukaya category of a surface. So an oriented surface, possibly non-compact with cylindrical ends and together with an area form so that it's officially a symplectic manifold. We should also choose a complex structure, but in this dimension, the choice doesn't matter at all. More importantly, we should choose a Hamiltonian function that controls this thing called the wrapping at infinity. So sigma has cylindrical ends with coordinates r in the real direction, theta the angle direction. We can assume the area form is kind of standard in these coordinates. And then we take a Hamiltonian function which grows, say, quadratically with r. All that matters is faster than linearly. We'll do it. So the objects of a wrapped Fukaya category are going to be properly embedded homotopically non-trivial curves or arcs on our surface sigma. Embedded is easier, but you can pretty easily allow immersed curves or arcs, that's fine. Or you can consider something called twisted complexes of embedded curves or arcs, which kind of enlarges your category by adding some mapping cones. We will also equip those objects with unitary rank 1 local systems. So what this amounts to for arcs, this is trivial. For closed curves, this amounts to the data of one number called the holonomy of a local system. Now, to be careful, I will be working over the Novikov field. This is a non-Archimedean field of power series in one formal variable t, with the particularity that the exponents are real numbers, but have to go to infinity. So we consider power series with countably many terms whose exponents, there's only finitely many terms below any given power of t. And the coefficients can be really in any field you want for this talk. Yeah, even of characteristic 2 if you wish, that's actually fine. All right. So then the local system is asked to be unitary, which means the holonomy is the unitary part of a Novikov field. These are things of valuation 0, which means the leading order term is actually a constant term of exponent 0. So if you want, these are the invertibles of a Novikov ring. So we want to have morphisms in a Fukaya category should be intersections of Lagrangians after we agree on some conventions about how they will intersect, specifically for non-compact Lagrangians, how they should intersect at infinity. So the so-called wrapped Floer complex of a pair of Lagrangians, Lagrangians is the technical term. If you really don't know any symplectic geometry, it's just curves or arcs here. Okay, there's no symplectic prerequisites in this talk. Is a chain complex generated by intersections of L0 and L1, except after pushing L0 by something called the Hamiltonian flow of this Hamiltonian H. And what this amounts to is basically something that you just, in each end, you keep R alone, but you increase theta by the derivative of H with respect to R in that end. And so because this grows faster than linearly, what you're doing is you're wrapping things more and more and more around cylindrical ends, hence the wrapped name. Okay, so these Floer complexes carry a Z grading if the tangent bundle of sigma is trivialized. That, of course, can only work on open surfaces or on tori. And otherwise, it's only Z mod 2 graded. I will not tell you about gradings because that's the one actual technical bit of symplectic geometry in this talk. So because in the ends we push things around in the theta direction, the generators of the wrap Floer complex are of two kinds. There's interior intersections of L0 and L1, and there's what you might call chords of the theta direction vector field near infinity from L0 to L1, rotating in the positive direction. And so this asymmetry in the wrap Floer complex is a big difference with, say, compact Fukaya categories. And despite that, the algebraic structure of wrapped Fukaya categories is arguably simpler than that of compact Lagrangians only. All right. I just realized I cannot actually see the chat while sharing. So if anybody has questions or things, you should probably speak up in case. Okay, so what does, so these morphism spaces in the Fukaya category, actually, maybe I can do something. Whatever Zoom is. Yes, I can. Okay, I can now see the chat, for I see that nobody has asked questions in there either.
Yeah, I should ask a question. In which sense is it simpler?
It's simpler in that it's more likely to be, well, for example, it's actually a smooth category, which means it has finitely many generators for a compact Riemann, for an open Riemann surface, in a way that if you look, say, at the, sorry, what do I want to say? Yes, if you look at, say, just closed Lagrangians, even if you ask for exact Lagrangians, but you allow local systems, then there is not a finite set of closed loops that generate the category. And if you want under mirror symmetry, that's because compact Lagrangians correspond to compactly supported coherent sheaves. And on an open curve, these are very badly behaved. I mean, well, they're very simple. They're just sheaves supported at points, but then there's no nice algebraic structure to that. The other answer, which will be clearer later, is that you can cut things into pieces. And when you cut things into pieces, you have to allow non-compact Lagrangians. All right. So the Floer complexes are chain complexes that carry a differential. The differential will be kind of not that crucial to this talk, but convention dictates that one should mention it. So it counts holomorphic disks with boundary on a pair of Lagrangians, in our case, after perturbing either the boundary condition, namely we push L0 by the Hamiltonian, or perturbing the holomorphic curve equation by the flow of our Hamiltonian H. But you should imagine that this has to do with when we look at L0 and L1 pushed in correct position by the flow of H, are there pairs of intersections that look like they should be able to cancel out? Okay. So whenever we see such a disk, we will say that this contributes to the coefficient of Q in the boundary of P. And the contribution is an element of our Novikov field, which has to do mostly, well, there's a sign. I will not tell you how to assign, decide whether it's a plus or a minus. It's actually complicated. And then an element of the Novikov field, which is a power of this variable T with exponent something called the energy of our disk. So the energy in the usual setting would just be the symplectic area, the integral of the symplectic form on our disk. But we are going to actually correct it in this case by some amount called the action of the generators, which is basically the area that has been swept in this Hamiltonian isotopy that brought the Lagrangians to whatever positions they were in. And then there's the holonomy term. So, we have local systems. We can pick trivializations at the marked points where the Lagrangians intersect. And then we just take the holonomy of parallel transport along the two boundary pieces. There are choices needed to do that. So if you prefer, there's also a more canonical description, but I think it's not really useful. All right. So basically, okay, this was just a prelude to actually the composition of morphisms, which is what I will focus on much more. So composition in a category involves morphisms from, say, objects L0 to L1, L1 to L2, and we compose them to get a morphism from L0 to L2. And so those will actually count holomorphic triangles with boundaries on perturbed copies of our Lagrangians, pushed so that each one is more wrapped positively than the next one. Or if you prefer not to move your Lagrangians, solutions again of a perturbed holomorphic curve equation. The advantage of a viewpoint on the left side is that this is just counting immersed polygons with convex corners. And so this is completely combinatorial once you have redrawn your Lagrangians in correct positions, except for the area part, which is geometric. Okay, and we built actually an infinity category, which means there are higher products that are of no relevance to our talk, except they're important for things to be correct, but I will not tell you. I mean, they just count polygons with more corners. Okay. So here's the basic example that I will use to motivate, first to illustrate the definition and then to motivate the slogan that I want to push as a way of understanding mirror symmetry. So basic example is the cylinder, R times S1 with a standard area form. And I claim its mirror will be, well, I mean, smarter people than me call it GM or something, but I will call it K star anyway. It's like the analog of C star of the Novikov field. It's all the non-zero elements of the field. Okay. So, so what do we do on a cylinder? The main object of interest is just a ray that crosses the cylinder straight. I'm calling that L0. And the theorem of Abu Zaid says that this generates the wrapped-Fukaya category. So that means every other object can be expressed as a mapping cone of L0 with copies of itself. And so if we understand L0 really well, we understand everybody. Okay, so if we push off L0 by wrapping, it all looks the same, but you should imagine that somewhere there's like a middle portion of a cylinder, which is like where our Hamiltonian is actually small, and then it grows towards both ends. And as the Lagrangian gets wrapped around itself many, many times, you get infinitely many intersection points that I will label x0, x1, x2, and so on to the left, and x minus 1, x minus 2, and so on to the right. If you prefer not to perturb the Lagrangians, these are just chords near either end of the cylinder that rotate around the cylinder in the theta direction a certain number of times and go from L0 back to itself. And then the one in the middle, x0, is harder to explain here, but it's the fundamental class of L0, basically. Okay, so the claim is right now, as a vector space, the Floer complex of L0 with itself is an infinite dimensional vector space. And so as a vector space, it's the same as Laurent polynomials in one variable x. Now, that is kind of a weak claim until I can actually say something more, which is this is actually a ring isomorphism. And so that's why I used that notation. So how do I check that? Well, the answer is I would have to study the product, which means having 3 copies of L0 perturbed to wrap faster and faster. And I will look for triangles. And a small combinatorial exercise here is if you look at any 2 pairwise intersections of the one that wraps at speed 2 with the one that wraps at speed 1, and that one with the one that doesn't wrap, then there's a unique triangle drawn on the cylinder with vertices at these two intersections, and its third vertex is at the intersection of L0 with the thing that wraps at speed 2, that starting from the center is at position I plus j. In terms of these chords in the theta direction, we're just saying that multiplying a chord that goes I times around with one that goes j times around gives you one that goes I plus j times around. And that's not very geometric, but it's actually easy to check by writing Floer's equation. All right, so why is this good? Well, this is good because this matches the structure of algebraic functions on what you can call the algebraic torus of dimension 1, if you want to be pedantic, or I will just say, call it K star. So this is actually the bulk of the proof of homological mirror symmetry for the cylinder once you realize that L0 corresponds to the structure sheaf of the mirror, and everybody can be understood in terms of modules over these objects, hence modules over this ring. All right, but let's be less algebraic and more geometric, because my goal is actually to push back against the tendency to make homological mirror symmetry algebraic. So I want to think about the points of the mirror. And so these will correspond to skyscraper sheaves. So if I can take a point Z in K star, I will factor it out for geometric reasons as something of valuation 0 times a pure power of t. So I want to factor out basically the leading order term and leave the rest as a factor. So the claim is geometrically this corresponds to a circle which is at position A in the R direction on my cylinder. This is because I normalized my area form in a very specific way, and my S1 has unit length. The correct answer would be it's the circle that separates, that is area A away from the central position, equipped with a local system whose holonomy is this remaining part C. So if I want to understand how this interacts with L0, well, I can calculate the morphisms between L0 and this object in my wrapped Fourier category. The answer is they intersect just in one point that I will call E sub z. So this is just a one-dimensional vector space generated by E sub z. And you can wrap or not wrap, it doesn't matter. It's all the same here. Now, what's interesting about this one-dimensional vector space is it's not just a vector space. It's a module over the endomorphisms of L0, because I can compose morphisms from L0 to L0 to Fz and ask, what is this composition? And so that means what I have is not just a one-dimensional vector space, but a module over Laurent polynomials. So I need to know, how does multiplication by x or by x inverse or by any power of x act on this one-dimensional vector space? And so for that, I look at my picture, which now has two copies of L0, one of them wrapped in relation to the other, and a copy of F sub z. And then I need to look for triangles connecting them. So for example, x to the 0 just has this little triangle that goes like that and maps visibly easy to what used to be easy under just the slight isotopy here. Well, it's not very surprising because x to the 0 is meant to be 1, which should act by identity. What's more interesting is what happens if I let, say, x to the 1 act. So now I look again at this. Well, there's again a triangle, this bigger orange triangle. And it still maps easy to that guy here, but now there's a large amount of area and holonomy involved. Okay. Another way to picture this, if I don't perturb my Lagrangians, is I multiply a chord near infinity with E sub z to get back to E sub z, and then the map looks like just this portion of cylinder that ends at F sub z. Either way, we have to figure out things about, okay, so there's a holonomy contribution and there's an area contribution. The holonomy part is the easiest. The boundary of this here goes once around F sub z. if I had taken x to the k, it would go k times around f sub z. So I said the holonomy is this constant c, so I get a c to the k. Similarly, now the area. So the area is, remember, corrected by action, which means I actually start measuring my areas when I hit the midpoint of the cylinder at x0. And then to the right of this, the amount of area is basically k times the area of the cylinder here, because this is like a k-fold cover of my cylinder. Again, same thing here if I'm at r equals 0, and then this area. So it will be k times a. And these two factors combine to give me z to the k. And this is a general phenomenon, like quantities of this shape that combine symplectic area on a surface with the holonomy around the loop are exactly how we get analytic coordinates on mirrors of, well, in this case, of cylindrical pieces of surfaces. In higher dimensions, if you have a Lagrangian torus fibration, basically the grown-up version of SYZ mirror symmetry says exactly you can do this similarly in families, now with more variables because it's a higher dimensional torus fibration. All right, so we've actually checked now by hand that x to the k acts by multiplication by the number z to the k. The difference here, x and z, they're the same thing, but x is the variable and z is the constant. And so now this means our module is actually, well, it's the rank 1 module of Laurent polynomials on which x acts by multiplication by the constant z. It's this quotient, and that corresponds exactly to the skyscraper sheaf of a point with coordinate z as a module over functions. You know, sheaves on the complex side are just modules over the structure sheaf. All right. Let's see, who's not confused yet? Any questions?
Yeah, can I answer one question?
Yes.
So how do I know that the ring composition xi times xj equals to xi plus j if I worry about the areas of the triangle?
So the fast answer for you is, you know that these are actually all exact Lagrangians for the standard exact structure. And so the areas will be exactly canceled out by the actions of the generators. Okay. So I was sloppy in not telling you how do I define the action of a generator. Okay. Anyway, there's a really annoying, it's a really annoying calculation actually, but anyway, we can try to do it if you want, just to check that the area of this triangle is indeed equal to the difference of the actions of the various generators. And so after rescaling, it all cancels out.
And in the last one, xk acting on EZ, you said it's the area sandwiched between the circle and of Z with a central circle. Mm-hmm.
So what I actually mean by that is, in the right side picture, when I take the action of this chord for a Hamiltonian lives at a certain position of the r coordinate. Yes. And the interpretation of its action will be actually the amount of area to the, between that and the exact position.
Okay.
And so that means the symplectic area corrected by action will just count the area from the central position.
Ah, great.
Another way to think about that is Fz is area A away from being exact. And so if you know this guiding principle that if you choose a Liouville form and then all the contributions will cancel out for exact Lagrangians, you see that what you need to ask is, how does the area differ from the exact situation?
Okay. Maybe another question, sorry to ask too many questions. So how much of this depends on the choice of the exact structure?
None, which is why I'm not mentioning exact structures.
Okay.
So and part of the slogan here is we don't actually need exactness.
Okay, great.
We need, so when we talk about these rescalings and so on, we need to choose a locally exact structure, or we need to be kind of more careful about our conventions.
Yeah.
Another way to do it is to just not rescale by action, but then like all the formulas that I want to make look simple here would look ugly, and they would be the same under some suitable rescaling. Okay. Even in the non-exact case, even on a closed Riemann surface, there are conventions you can choose to kind of rescale away all of these arbitrary constants and make things look neater.
Okay, thanks. That's all my questions.
Sure. All right. let's continue. The hopes of getting somewhere. So the slogan of the talk is very much in the spirit of actually what's known as the family Floer program, which has been pushed by Fukaya first and then developed more carefully by Abu Zaid over the past decade. I would say Fukaya was the 2000s and Abu Zaid more recently. And the idea there is that it's advantageous to think of Floer homology as, with a family of circles, or more generally of tori in higher dimensions, as a way of testing what happens at different points of a mirror. And so the slogan I want to give here for our case today is if I have a Riemann surface and it has a cylindrical portion, let's call that U, which I will choose to identify by some choice of coordinates. I should have said area preserving, so that omega looks like dr d theta, with just a modeled portion of cylinder. And let's say that I also have two Lagrangians L0, L1 that run parallel, alongside each other inside that neck. So the claim is there's a nice geometric interpretation to what we can do with that neck on the mirror. On some mirror, I should say. So there's not necessarily a unique mirror space, but on a preferred mirror in relation to this cylindrical structure. So the first statement is that we have a chart on the mirror space, which is modeled on what's called an aphenoid domain. That's a fancy word for, it's the generalization of an annulus. When you're not, in complex numbers, people talk about annuli. And this is like a non-Archimedean annulus. These are things whose size is between two constants. And this local analytic coordinate, z, will be corresponding to looking at a family of circles, just like the points of a cylinder that we discussed before. We look at all the S1s in this cylindrical region with all possible unitary local systems of rank 1. And we define a local coordinate by just taking the holonomy times t to the a is the value of this r coordinate. Of course, so that means a is a proxy for how much area is between my given f sub z and some reference position, which is arbitrary. So if I change my reference position, z gets scaled by a multiplicative factor, some power of t. And then L0 and L1, what do they correspond to under mirror symmetry in this local picture? Well, they are objects whose homes with any Fz is of rank 1. So that means they correspond to sheaves whose home with any skyscraper sheaf is of rank 1. That's essentially line bundles on the mirror, or at least on this piece of the mirror. Because I asked that my two Lagrangians should run alongside each other, I mean, I drew them slightly separate, but I really mean for them to be almost on top of each other. Moreover, I have not only two line bundles, but I have a fixed isomorphism between them on this portion of the mirror. And that will allow me to talk of sections of, L0 dual tensor L1, if you want, morphisms from L0 to L1 as functions on this piece of a mirror. That's why I want trivializations. Okay, so for example, an intersection S between L0 and L1 that lives somewhere far away. I didn't want to put it too far away so we don't lose sight of it, but it could be very far away on the surface, is now going to correspond to a section of the difference of those two line bundles, and now I can try to evaluate it at points in my cylinder. And what I will get is something very similar to the picture I had drawn before, just on a global cylinder. I have a holomorphic now triangle that starts at S and goes from S somewhere along in my surface, and at some point it gets into the neck. And now I can choose to stop it at Fz and produce a holomorphic triangle with corners at S and these two intersection points here. what the count of such triangles does, if I look at all possible configurations, all possible homotopy classes, and so on, is tell me the value of S at the point Z on the mirror. And so now by the calculation we just saw, if one of these disks comes in and enters the neck in a way that wraps k times around the S1 direction, then we'll get something that behaves like Z to the k. When we try to evaluate it on a particular Fz, as a function of Z, it will vary like Z to the k, by exactly the calculation we had here on this example. And so that means the count of such disks which propagate whichever way they must and then enter this region with wrapping k times in around the S1 factor are going to be the coefficient of Z to the k in the Laurent series expansion of S on this piece of the mirror. And that's probably something that physicists were well aware of, and they probably had words like propagating modes of vibration of a string or something. But I think mathematicians kind of lost sight of that, and so I'm trying to kind of reintroduce that a little bit. Again, this is nothing fancy compared to what happens in family Floer. This is just like one little concrete piece of it. And similarly, if your instead S kind of maybe has something that comes here and then that goes around some other part of the surface and that comes back in here, something that enters from the right of my neck with my convention corresponds to negative powers of Z. And of course, there's nothing special about left and right. It's just a choice that my coordinate Z goes one way. I could use Z inverse as a coordinate just equally well. All right. Questions? It's hard to question a slogan. There's no statement here. It's just a philosophy. So let's move on a little bit. Oh, one more thing, sorry, in relation to that. You might ask, well, but why did we have to choose a trivialization? I don't like trivializations of bundles. Well, the answer is you can change trivialization. How do you change trivialization? So first you can change trivialization by a constant factor, by just letting L0 and L1 temporarily diverge from each other, but then come back, without any actual twisting or anything. So then the amounts of areas or corrected areas measured here or measured here will differ by this amount of area. So this amounts to a change of trivialization that multiplies things by a constant factor. What's much more interesting, I think, is what happens if L1 twists around the cylindrical neck as it travels. So then you can try to trivialize on this, in this region that I call U, and in that one that I call V. And then you find that if some holomorphic disk enters this cylindrical region in a way that covers k-fold the cylinder on the left, as it keeps propagating through the neck, it will acquire one more loop around the theta coordinate. And so that means here it will become something that covers with degree k plus 1. And so what this means is any function that locally look like Z to the k, sorry, any section rather of a line bundle that look like Z to the k around here now looks like Z to the k plus 1 around here. That means we've glued together two trivialized charts of a line bundle with a transition function that's some constant times Z. The constant depends on exactly where you place the twist, how much area is in between, and so on. But that would bring me back to difficult questions about how exactly to measure areas and actions. Okay. And so if I were on a closed Riemann surface, sorry, on the mirror of a closed surface, rather, well, that's the same, that would happen degree of our line bundles times, just for topological reasons. If you think of a complex line bundle on a Riemann surface, it can be trivialized locally, but globally the trivializations will have to have this kind of twisting by a degree 1 transition function exactly as many times as the degree. All right. So next example. Now I'm back in 1998, the prehistory of homological mirror symmetry. So Polishchuk and Zaslow worked out in a very explicit way how to do homological mirror symmetry for the two torus by just counting triangles on a torus and matching that with theta functions. But now I can explain how this fits with my slogan. If I look at this picture, I have two circles, L0 and L1, which agree around my torus in most places, except at some point, somewhere L1 kind of goes once around what I consider to be my S1 factor of the torus. Of course, they're both S1 factors, but the one that I think of as the theta direction. Okay, maybe so this one is the theta direction. And that one instead is the R direction. And so now I can apply this is a good test case to make sure that things are not complete nonsense. L0 and L1 intersect exactly in one point, S. And I can ask, what is the value of S at some point of a mirror as instantiated by this fiber F sub Z with a local system? And so I need to start counting triangles between S, L0, L1, and FZ. So the first one is just like this tiny thing here, which will basically contribute 1. Its contribution is trivial. But there's another one which starts here and grows, comes back around to here, and eventually it gets here basically as what I would call degree 1. That means it just covers the cylinder once, it wraps once around. Okay, so that will be a Z to the minus 1. But there also are bigger ones, right? If I take the one I had started with here, and I continue past here, it's widened.
This cycle twice? I couldn't visualize.
Yes, it could keep going and go twice or 3 times or any number of times. So in fact, the statement is that the contributions, there's an infinite family of such triangles. I've only drawn really T0 and T minus 1, but well, I guess this one was the beginning of T1 here, and so on. So for every integer, positive and negative, there's a triangle that goes n times around the torus in both directions and ends up covering the S1 factor n times. Okay. Its area, well, you can calculate basically by just going up to the universal cover and counting how many tiles you cover. It's basically n squared over 2 times the whole area of the torus. So I should have said plus, of course, n times A, because that's, well, A is, the position of this FZ. Okay, and so that means we write, in fact, the Laurent series expression for S in terms of the coordinate Z on the mirror as sum over all integers n of, so there's this Q to the n squared over 2, where Q is the weight of the whole area of the torus, and times Z to the n. And this is a classical theta function. Maybe it doesn't look as classical here because I've written it in exponentiated form, but that's the same thing. So this is a section of a degree 1 line bundle on the mirror elliptic curve, which multiplicatively in terms of its coordinate Z, it's basically K star, where you identify together things that differ by multiplication by some power of Q. This is kind of another way of saying a torus is a cylinder that has been folded on itself by periodizing every now and then. Okay, and so it satisfies some transition function, which is the transition function of this particular degree 1 line bundle. That's kind of the change of trivialization thing that happens when you go all around the torus. Okay. So here I'm focusing on evaluation at points, but there's a similar story and geometry for multiplying functions with each other. And so when you want to prove homological mirror symmetry, you can really just do these very concrete calculations in this low dimension. If you are a fan of big, high-powered machinery, then I should mention that the Gross-Seibert program tells you how to do this in a much more powerful way using tropical geometry in higher dimensional examples. So this is just like a one-dimensional shadow of bigger things. Okay, so let's talk now about how we'll go beyond baby examples like that. So the goal is to have a local to global principle, and that principle is different from the one that's fashionable these days among symplectic geometers. And I would like to argue that they both have a role to play in the real world, but that this one maybe has, once it's better understood, it might have a bigger role to play than the other one. And I'll explain why in a moment. So the goal is to use these ideas to compare Floer theory on the surface with analytic functions on the mirror and prove concretely in a very by hand geometric way, but without doing too many calculations, homological mirror symmetry. using decompositions of sigma along cylindrical necks. And what does that mean on the mirror? That's decompositions into basically covers by affine charts, or rather affinoid charts would be the correct term in this weird non-Archimedean world, but maybe you don't need to worry about that. So the reason I think this is, okay, sorry, maybe I should tell you the next remark. So another way to decompose things on Riemann surfaces, on open ones at least, is to use the technology of sectors or microlocal sheaves. This is, so what I'm doing here, well, standing on the shoulders of other people, including my former student Heather Lee, is different because we don't need exactness. This actually works on closed surfaces without having to worry. Also, we cut our surface along S1s, and what we will get is restriction diagrams. We restrict from the big surface to the small ones, as opposed to what sectors do, which is inclusion diagrams, where you build, so basically ours is a sheaf, the other is a co-sheaf. And maybe the reason I'm attached to this one is that in algebraic geometry, it's very common to calculate things on smooth projective varieties by taking affine open covers and doing, say, some check complexes for that. And this is really what we do on the symplectic side here, as opposed to what you get from sectors, which would be more like gluing closed subschemes to produce a reducible space, which happens surprisingly often in affine mirror symmetry, but I claim will not be the right way to look at mirror symmetry if you want smooth mirrors, because they don't decompose into unions of closed subschemes. Of course, there's a way around that, even in that philosophy, by degenerating and deforming. But anyway, so the drawback of this approach is that right now it only works in dimension 1, but that is being worked on. Okay, so the key tool is basically to imitate check complexes and how you calculate global sections or cohomology of a sheaf by working on affine charts and asking about overlaps and compatibility conditions at those. So the symplectic counterpart of that is a result from the Berkeley thesis of Heather Lee, but 2016, it's like 6 years ago, but it's still useful. So the idea is if you cut a surface sigma along cylindrical necks into pieces, then there's actually, so Heather Lee's construction produces a model for the Fourier category of sigma in which all the holomorphic disks will remain inside a single piece at a time. And so there will be restriction functors just by discarding all the stuff that's not inside one piece of your decomposition. And what's interesting is that this category will be actually equal to the limit of this diagram. So this is a possible way of computing, or for proving equivalences, it's just the exact counterpart of acyclicity for check complexes and the way that you calculate basically using a check resolution in an affine cover. Okay, so how does this work? So setup, start from a surface decomposed into pieces indexed maybe by the vertices of a graph.
Can I ask a quick question?
Sure.
So this Novikov ring stuff, I'm thinking of this, and maybe this is wrong, as working in a formal neighborhood of the semi-flat limit. Is that where this t coordinate is measuring how far you are from that limit? Is that fair?
Essentially, yes, you could say that, or without saying semi-flat, you could just say, yes, t measures basically a deformation away from the large volume limit on sigma, large complex limit on the dual, yes. It's a convenient way of not asking whether the mirror is an actual scheme rather than a formal scheme. In practice here, it's always something that will converge. But,
right, so this is exactly what I wanted to ask, is there some analytic condition that tells you, because for like the torus example you worked out, those functions actually converge, right? So
yes. So I think basically, it boils down to the growth rates of the numbers of triangles or polygons of a given area with the size of the area. The answer is, in practice, if you're trying to calculate just products or things like that, then there's never any problem on Riemann surfaces. In higher dimensions, you can cause some trouble. What's more problematic is continuation maps or invariance under Hamiltonian isotopy, which symplectic geometers are very attached to. You can produce divergent continuation maps that should be isomorphisms and don't in Floer theory.
Is that like some this failure is because like one is ignoring some wall crossing or something, or where's this divergence coming from?
Sorry, I think I need to take that back. It's a lack of uniformity of a convergence, because if you allow all Lagrangians at once, you might run into polygons that are thinner and thinner. So basically, you might encounter families of rectangles or other things that are extremely thin if you let your Lagrangians vary. One way around that is to fix a collection of Lagrangians in advance, and then you don't have that problem in dimension 1. In dimension 2, you have problems because sometimes, if you count things that are sections of a bigger fibration over a base, you might have small polygonal regions over which sections exist in a way that, the combinatorics of how many holomorphic disks exist can explode if you make it explode. And so you can produce divergence there. But it's kind of artificial. Real life examples want to be convergent, I think. So I think you should not panic over it. But basically, since there's no good mathematical theory for it, I think in dimension 1 it could be proved if people bothered, but people don't seem to be in a big hurry to bother to prove it.
I guess if you know that you have a mirror, then you should have nice answers.
Yes, exactly. Yes. For the question is like, is your mirror going to be a formal scheme or an actual curve or something? And yes, but it turns out to be an actual curve. So that's in real life, there's not too much trouble.
Sorry, maybe I have a question. The Hadley's paper was about like affine case. So you're saying the same.
It doesn't use affineness. Yeah, it's stated in the affine case, but the proof doesn't need it. You can see a non-affine version of that in my paper with Ivan Smith
right.
on 2020, section 5, I think, does that.
Okay, great.
Anyway, so I'm attributing it to her because it's really the same proof and the same statement. But okay, so the statement is, okay, so I have a bunch of pieces. In her case, these are pairs of pants, but you could take any Riemann surface that's not a disk. Disk is the only thing that's forbidden. And they overlap with each other along cylindrical legs. And so we can encode that by a graph if that kind of makes you feel happy. There's vertices for the pieces and edges for the overlaps. Then anyway, the statement is there is a notion of restriction functors from the wrapped categories of the pieces to the wrapped Fourier categories of the cylinder for each vertex adjacent to an edge. And the wrapped Fourier category of the big total space, of the total surface sigma, is in fact the limit of this diagram. So it fits in a pullback diagram. So in fact, this is like, okay, so you can ask, what's the limit of diagram of categories? And the answer is, I don't really know any more than you do, except Peng, who probably knows very well. But here's a very simple explanation for what actually happens. But just to say that this corresponds also to a check model for calculating on the mirror, basically. So this is actually a very concrete kind of limit. My favorite kind of limit of diagrams of categories is one that you can actually calculate by hand, almost. So the idea of a construction is to use large Hamiltonian perturbations. Oh, sorry, I should also mention there's a related paper of Paskalev and someone, so I should have looked it up, that does the same, essentially the same thing in a different way. Anyway, so see also Paskalev plus question mark. Sorry to question mark, especially if you're here. Sorry, do you know Peng actually? Who?
It's Niccolo Sibilla.
Oh, Sibilla. Sorry, yes. Okay, of course. Okay. All right. So anyway, so in Lee's version, you use a large Hamiltonian perturbation in each cylindrical neck. Okay, so that Hamiltonian will just be constant inside each piece, roughly, constant inside the neck, but it will dip a lot down at the edge of the neck. What that does in terms of wrapping is an arc that wanted to run quietly through a cylindrical portion will get first wrapped very strongly in the negative direction as the Hamiltonian dips down, then back in the positive direction when it undips. At this point, it has done as many turns backward as it has done turns forwards. So here it's back to its original place. Then at the other side, we do the opposite. First dip forward, then dip backwards. So this is negative wrapping, positive wrapping, positive wrapping, negative wrapping. The effect of this is basically any holomorphic disk that wanted to cross through into this neck is going to actually get squished by the negative wrapping at some place, unless it had inputs inside the cylindrical neck itself, not shown for clarity. But even then, there's going to be some very strict restrictions on what can happen. And what Heatherly shows is that there's no way that a holomorphic disk can cross both edges of this cylinder. So this is in fact an impenetrable barrier for holomorphic disks. So the statement, before we talk more about the statement, so what happens in this perturbation, of course, is we create a lot of new Floer generators with all these intersections. Here we create Floer generators in degree 0. Here we create generators in degree 1. And between them, there are Floer differentials that cancel them. So you might say this is like a homological algebra nightmare. We create lots of generators, lots of intersections. But the advantage is that now holomorphic disks are local within any piece. So what you can get furthermore is that the generators that are not in, say, sigma v going all the way to here, or not in sigma v prime going all the way back to here, or in fact not in the cylinder, span what's called an A-infinity ideal. That means the output of any Floer operation involving one of those is also one of those. And so that means you can quotient by them and be happy about just discarding them and never looking at them. And that means you see inside this perturbed version of the wrapped category of sigma, just by focusing on the geometric pieces you need, exactly on the nose chain level models for the wrapped categories of the pieces. And what is the restriction? From sigma v to u sub e, it's just forget everything that's not in u sub e. Okay, so and now the statement that you have a limit of a diagram is very concrete. Morphisms in sigma are just morphisms in this whole diagram. So they are exactly morphisms in any of those pieces, sigma v, but with the requirement that if I have a morphism here and a morphism there, and they contain some of the generators in the neck, then they must have the same copies, the same coefficients of the same generators in the neck. So it's just things that on the nose agree under restriction, which is much nicer than a random limit of a diagram of A-infinity functors. Okay, so to return to what I was also trying to say, a Floer generator, that lives outside of this neck might try to produce holomorphic disks that go into the neck as a way of telling you what it would evaluate to as a Laurent series in this region. Well, the same disks that enter into here and to help us evaluate it as a Laurent series, now instead they die before they enter the perturbed region, which means this generator S will no longer be closed under the Floer differential because d of it will be somewhere here. How do we make it closed? Well, we need to add to it the canceling generators on the even side, on the inside the neck, that cancel out those things. So, sorry, if I unscribbled all this, S that produces this yellow disk, you need to add to it this thing here, which by the red disk will cancel out. And what do you get inside? What you get inside is exactly the Laurent series expansion of the section from outside. Which is why I say a Floer generator that lives outside of the neck gets corrected by adding to it a sum of the generators inside the neck, which exactly give its power series expansion.
For this, you need to wrap positively and negatively infinitely many times?
Yes, it's a limit over wrapping arbitrarily many times. So when I said everything is explicit and so on, it's explicit if you're willing to consider wrapping infinitely many times. Otherwise, you can compute order by order.
Homomorphic functions from 3D.
Yeah. Otherwise, you can compute order by order, basically.
Sorry, I have a question about how to deal with that infinite wrapping. Because if you wrap just for a large finite amount of time, you can always find some like a chord that wraps even more outside of it to try to send stuff this into that cylindrical region, right?
So the statement is whatever you want to calculate involves some Floer generators that existed before you did the perturbation. Okay. And so there's one assumption you need to make. If you exclude closed curves that live outside of the cylinder but are parallel to it, those have to be dealt with separately using their own rules. But everybody else, if you only use Floer generators, arbitrary Floer generators, and you try to calculate their mu k, some Floer product between them or differential, then the degree with which things enter this neck will be bounded a priori by quantities that only depend on the input generators.
Okay.
Sorry, and the path that you choose to travel in the graph. So the claim is this is suitable for an order by order expansion. That's going to be fine.
Okay.
I don't think that has been stated in this way in Heatherly because she just proves HMS, but the order by order expansion, well, I mean, there's an alternative argument in my paper with Efimov and Kaczarkov also. Okay, so where this was going, but I don't know, it's kind of been an hour, so maybe I should try to wrap things up. How do you guys, what are the rules here?
We're always flexible with time. We let our speakers tell their stories.
Okay, but okay, so anyway, I'll try to keep telling things, but maybe I'll try to be efficient. So more interesting building blocks come up when you don't look just at cylinders, you need other pieces. So one is the pair of pants. Okay, pair of pants, easy to deal with, and on the face of it, it's a cylinder with an extra hole in it. So you can copy what we did with this L0, calculate its endomorphism ring. The main difference is you're no longer allowed to look at triangles that live over this region, because this is no longer a valid holomorphic disk because of a puncture. And so that means what you will get is that the generators on this side and those on that side now multiply to 0. And so instead of Laurent polynomials, I get polynomials in two variables which multiply to 0. And the mirror indeed looks like xy equals 0, the union of the two coordinate axes in affine space. You can also do this trick of evaluation. If you have something that evaluates here to a power of x, you see that no disk will be able to pass through. So here it will evaluate as 0. But anything that would have wanted to come in from that side, vice versa, will be a polynomial in y, but will be 0 on the x side. Okay. So the interesting thing, though, is that there are also objects which end at the third puncture and are not really accounted for yet. And what they correspond to is objects of a coherent category of coherent sheaves on this mirror thing that are not perfect modules. That means not expressible by vector bundles on the whole thing. So a basic example of that is these two curves, L1 and L2, that I've drawn on my pair of pants. If you try to, there's actually a threefold symmetry in the pair of pants, so you can calculate their endomorphisms, and you'll see that it involves these powers of x, which are kind of chords that go around this end, but also now powers of a new variable that I will call z, corresponding to that end. And so, if you calculate a lot, you'll find that morphisms from L0 to itself, so the Floer complex is just polynomials in xy with xy equals 0. This corresponds to functions on this. For L1, you'll get something similar in two variables x and z. For L2, similar in y and z, with one important thing, that the degree of z, for whatever z grading we have, has to be 2 if x and y have degree 0. And so the interpretation of that on this xy equals 0 is as the structure sheaves not of a whole curve, but of one of the two components at a time. Okay. And those have indeed x in all even degree, forming a polynomial algebra in this z generator in x2. So I'm using the same letters X, Y, and Z for all of those because I haven't told you, but these are all, morphisms between two of those are bimodules over all these algebras and so on. And this fits consistently into some geometric picture. So the more symmetric description of a mirror, I would argue, is, well, we can let go of the Z grading and work with a Z2 graded category. And then I would argue that the curve xy equals 0 has, in fact, extra Z2 graded point on a Z coordinate axis. In the sense that these are modules over this algebra. They're not Z graded modules, but they're Z2 graded derived modules, something. Anyway, maybe a more ordinary way to describe that is this is also the critical locus of a function xyz on affine free space. And so there's a mirror symmetry statement that says to your choice that the Wrap-Fourier category of a pair of pants looks like coherent sheaves on xy equals 0, or that it is matrix factorizations of the Landau-Ginzburg model on affine three-dimensional space with a function minus xyz. So you look at how these things multiply with each other. So the advantage of having given Z first-class citizenship is now we can evaluate functions at points on all three legs. Because we can pair with the circles at X, at Y, and at Z. And these would not be objects of a Z-graded Fourier category altogether. There would be a grading obstruction. But on a Z2 graded Fourier category, they're fine. Just like all three kinds of points are fine on a Z2 graded scheme.
Sorry, can you say a bit more? What do you mean by Z2 graded point of this scheme?
So I mean, usual theory of coherent sheaves on xy equals 0 would be, modules, nice, whatever, finite generated, something, modules over the algebra k bracket xy mod xy equals 0.
Sure.
And now I want to look instead at Z2 graded complexes of modules. Okay. Let's just say Z2 graded DG modules over this.
Okay.
And so what that does is, there's this Z which lives in the X of these ordinary modules. I'm now allowed to take the cone of Z minus a constant or something like that, which would not be graded. And cone of Z minus a constant is exactly what I need to produce a point on this Z leg.
Should this be equivalent to changing the holomorphic form?
So yes, this is equivalent to allowing myself a lot of flexibility in how I trivialize the tangent bundle or what holomorphic one form I choose on my pair of pants and at which two legs it will be trivial, and allowing myself basically all the possible flexibility about that. That's exactly how you can think about it on the symplectic side. And on the algebraic side, it's reduce all the degrees mod 2. All right. Okay, so just to summarize what Van Heverly's construction does is starting from the statements about the pair of pants, you can assemble pairs of pants together in really any way you want. So given any Riemann surface with a pair of pants decomposition, I guess that means it needs to have negative Euler characteristic. Then you can produce a mirror by gluing these kinds of pictures. In her work, this is like Landau-Ginzburg model C cubed comma minus XYZ, but you can think of it differently. And then you get a mirror symmetry equivalence between those. And so the proof reduces just to the case of a pair of pants using restriction diagrams. Her result was only stated for affine curves in C star squared, where the mirror is a toric Calabi-Yau threefold, so something that like Minna's favorite class of examples of mirror symmetry. But the proof actually works for any pair of pants decomposition of any surface. It's just that when you don't have this global assumption, the mirror is kind of just something glued from local charts, and you don't really know as easily what to call it geometrically. It's the space built by assembling these weird charts, which are not even like honest spaces because they're like Z2 graded something. Or you could say glue together Landau-Ginzburg models, but then good luck explaining really what that means.
So you don't have a global Landau-Ginzburg model on B side?
I think there's probably one, but I'm not completely sure. So, in the case of curves in C star squared, there definitely is one. And for closed curves, in fact, there is one because you can produce one by hand from other methods. But, and it decomposes back in this way once you stare at it. But, a priori, it would not be obvious really whether this is a global Landau-Ginzburg model.
Okay.
How many branes do you need to generate a category? Like if you have a genus G surface with
just anything that decomposes it into polygons. So the basic argument that follows in a way from Abuzaid's generation criterion is if you have a collection of arcs or curves that cuts a Riemann surface into a union of pieces that are all polygons, then it split generates. So really the condition is enough to cut things, enough to cut the topology all the way into polygons. So by polygons, I mean polygons allowed to have ideal corners. So for example, on the pair of pants, in fact, to generate, you need 2 of the 3 curves I've been focusing on. That's enough to cut it into something polygonal.
So in your proof with Evan Smith, do you need to consider global generators on the figures or just local ones on the pair of pants? Like these arcs, do you need to consider like closed loops?
So what Heatherly does is basically consider this arc, this arc, this arc, and show and versions of these arcs that twist around, which is enough to generate closed loops that go around. So what Lee does is really consider things like that, but when you glue them across pairs of pants, you allow them to twist in the neck, which means in terms of generation, this is the same as having a collection of things that just run around like that, and also the separating necks.
Okay.
So that cuts things into hexagons or something like that.
Okay.
But in principle, you could also just state it. You don't actually need to look at the generators because you could just say, category matches the category. You could just look at the local generators. Once you have restriction diagrams for the categories on both sides, that's good enough. Anyway, so the thing I wanted that was supposed to be the punchline, was the mirror of that, which means what if I put this on the symplectic side? So my first way of describing it will be again, xy equals 0, now in C squared, because we want an honest complex surface, complex curve. So this is like a nodal cylinder. You can ask, what is the Fourier category of this? First, why do we care? Well, why do we care? The answer is because that way the mirror will have a pair of pants. Before that, I had on the symplectic side any genus, but on the complex side, just like these funny trivalent configurations of P1s and things. And now we need to switch that around. So the Fourier category of a nodal cylinder, one possible definition explored in the paper of my student Maxime Jeffs is, well, this is a singular hypersurface. It has a smoothing by xy equals t, which is cylinders, and the vanishing cycle for the degeneration is just a curve around. So the slogan is you're supposed to be able to define the Fourier category of a singular hypersurface by just smoothing and then quotienting by the category of vanishing cycles. And so you can do a calculation. Quotients of infinity categories are a bit of a monstrosity because what you do is you actually keep the objects, including the ones you kill, but what you do is you introduce extra morphisms and differentials between them. You declare that Homs in the quotient category between any 2 Lagrangians will be not only the Homs you used to have on the cylinder, but also all sequences of Homs through the object you want to kill. But there will be a differential on that, which is given by Floer products. So the idea is any morphism that can be factored through the object you're killing becomes the 0 morphism. You should think of it as killing morphisms that factor. So you can do geometry with that because, these correspond to intersections, and the new ones correspond to, in fact, you travel on L0, then you cut at this reference fiber, you put a bunch of marked points for this, go back on L1, and you can count these just as well as any other kinds of polygons. It's just that these become new versions of the polygons that I've drawn like that. Okay, and of course, this thing is actually the neck of the cylinder. So actually it will look like this. But in here, I need to talk about what happens. Okay, and you can actually evaluate explicitly and find that these new generators correspond to these kinds of Laurent series. This is to one side. There's a power series in Z to the K, and there's one in negative powers of Z, depending on which side you try to go to. And so what this shows is really this corresponds to quotienting on the mirror modules over Laurent polynomials by allowing Z plus 1 to be inverted. So you quotient by the skyscraper sheaf at a point, and that's how algebraic geometers delete a point from a space. That's one of the ways we do it. Okay. But here again, the problem with that is that we are not being symmetric about the free ends of the pants. So one option is to say, well, really what we should have done was look at the Landau-Ginzburg model C cubed comma minus XYZ, and you can calculate the Vrat-Foucault category of that. Nadler was the first to do it using microlocal sheaf techniques. With Abu Zaid, we have a more convoluted, more purely symplectic calculation. Or more boldly, you can say, well, I'm going to work on this space, whatever it means. What it means now is actually a placeholder for something that sits in that Landau-Ginzburg model and allow objects of this shape. And so this is what my paper with Efimov and Orlov does. What we declare is we can just look at Floer theory in trivalent configurations of Riemann surfaces attached at nodes. We allow, so points on the mirror correspond to circles like these ones. And now the new thing is that line bundles on the mirror will correspond to trivalent graphs drawn on sigma, with one leg in each piece at each trivalent vertex. You could do also larger vertices, just that the mirror pieces would be not pairs of pants, but higher punctured spheres. So now we just wrap in each piece, in each leg, and we'll have 3 infinite series of generators if we try to wrap just the basic graph here, L0. Plus 1 generator at the vertex, that's a convention that I cannot completely justify. Right? It's a long calculation. And the claim is these generators here will correspond to powers, successive powers, of certain local coordinates on a mirror pair of pants. And what coordinates on the mirror? Well, the answer is there's no canonical choice. This may relate to the fact that secretly, my point Lagrangians here, they correspond to the so-called Hagenagich-Vafa branes in C cubed. And there's data called a framing choice when trying to just reduce their geometry to what you see in the coordinate axis. So somehow the model that we have inputs a choice of coordinate charts on pairs of pants for the local models. But then with that data, we can actually calculate. And what will happen here for this L0 with itself is you'll get 1 generator at the origin and a bunch of others along the coordinate axis, which will all be successive powers of certain functions. And those functions will just be the inverses of local coordinates near the punctures. So if you think back about partial fractions as a way of understanding meromorphic functions on P1 with 3 poles allowed, poles allowed at 3 particular points, the punctures of a pair of pants, partial fractions tells you that they are indeed linear combinations of this additive basis. And so then what we do, I promise I will stop with this slide. What we do is we have a differential and products on Floer complexes in this setting that look at propagating configurations of holomorphic disks running through these trivalent vertices. And as they run through, so we count, of course, we keep track of symplectic areas and holonomies, but we also have multiplicities. The multiplicities are given by combinatorial factors, which are basically binomial coefficients in practice. They depend on the input degree. So all my Lagrangians actually touch each other. They arrive tangent to each other at the vertices. So when they enter or leave at a vertex, they will wrap around the angular direction and some integer number of times. This one, for example, comes in with degree 1, comes out with degree 0. So whenever I have that, what I want to do is this comes in representing some function, which is, in fact, z1 to the minus d1 in terms, it's a power of a coordinate on this leg. And so now, if I want to know how does it escape on that side, the answer is, well, take z1 to the minus d1. It's a function that has a pole of order d1 somewhere at that end. But here it's actually decaying towards 0. So I can expand it as a power series in z2 at the other puncture. And the coefficient of z2 to the d2 tells me how much I should count things that come in with degree d1 and come out with degree d2. So what this model does, it's actually cheating, basically. What you do is you build a model of Floer theory based on analytic continuation on a gluing of pairs of pants with explicit gluings, and each analytic continuation involves taking your input power series and re-expanding it into the next coordinate. The advantage is it's in fact almost tautological that homological mirror symmetry holds for this version of Floer homology, because it matches what analytic functions want to do on an analytic space glued from charts. What's actually the longest part of the proof is checking that these definitions make sense, define an A-infinity category. There's actually crazy combinatorial identities involving power series expansions and converting between different charts for meromorphic functions on pairs of pants, but it actually works out very nicely. So with all that, I'll just leave it as, the theorem supposed to, and this is basically, it tells you now if you have a trivalent configuration of just complex planes and P1s, and you can define a Fourier category of trivalent graphs in this crazy way. And this actually is derived equivalent to coherent sheaves on a mirror curve glued from basically domains in pairs of pants according to the way that your symplectic manifold was set up. Okay, it's high time that I finished. I think this talk, at least the official part. So I've said everything I had to say. Thank you for being so patient with me.
Thank you, Denis. Let's see, how shall we start this? What happens at vertices there when they pass through the vertex? What are the rules?
So the rules are basically you're allowed to pass. Okay, let me show you this example, for example, here. So this is like trying to understand functions on a punctured elliptic curve in a very roundabout way. So when you so basically the things are okay. So the objects, right? They are trivalent graphs, and they have one leg on each thing at a trivalent vertex. The holomorphic disks, maybe that was clearer here. They just pass through a vertex, jumping from one leg to another leg. Okay, so this is like a strip between A and B, a holomorphic strip between A and B. It's moving to the left. That's how symplectic geometers like to draw these things. Here it's a holomorphic strip between A and B. This is the input of the operation. It goes into a vertex. There's a special rule for if two things arrive simultaneously at a vertex and multiply there, then you take the constant term in the product. But the general case is if it comes in here, it's going to be allowed to come out in either of the two other legs. It has a choice, and it's allowed to come out with any degree it wants. It could do this, or it could actually cover this like 3 times or whatever. To decide what is allowed and with what multiplicity, what we do is we take z2 to the d2, we take z1 to the minus d1. So some monomial in the input coordinate associated to the input part of the disk. And we expand it as a power series in the output coordinate. Mm. And the coefficients in the power series tell us what multiplicities we count each outgoing degree with.
So what is the
this is kind of tautologically what needs to happen if you believe in the slogan from earlier.
I see. So you don't justify it, you just show that it gives rise to a consistent A-infinity category, and then you say...
That's right. So one of my students is working right now on kind of plugging that gap. He's actually calculating more carefully product structures in the wrap Fourier category of this Landau-Ginzburg model that corresponds to this, and checking actually what the generators correspond to very explicitly, and trying to make. So the difficulty, if you want, in understanding what exactly, whether this matches reality, is the Floer complexes here. In fact, on the pair of pants, there's no differential. You directly get an additive basis of functions. Most of the models that you can write that do not involve this fiction, they actually have large Floer complexes and differentials that kill most of the generators. So that, in fact, you only get equivalence classes of expressions for functions. So my student Jaewon Chang is basically working through the verification of this from the geometry of the Landau-Ginzburg model. So that should bring some clarity in whether this is actually what geometry wanted us to do. I think the answer is geometry wanted us to do something like this, but it might have chosen specific coordinate charts on pairs of pants that we didn't know. This right now has been set up with, like, for any choice of coordinate charts on a pair of pants, we can do this construction and it's valid. So what's not really known yet is what would be the canonical coordinate charts we should be using.
Sorry, one question. So what do you mean by expanding Z1 inverse in terms of in the neighborhood?
Okay, let's look at this example here. Let's say I want to calculate the differential of, so what is this? This is a mirror of a pair of pants, of a once punctured torus.
Yeah.
Okay, because I think of that as a self-glued pair. This is a pair of pants with self-gluing between two of the legs.
Sure.
So now what I should imagine is, so L0, like this blue graph, is just a structure sheaf, and I want to know functions basically on a punctured elliptic curve, which is the same as meromorphic functions on the actual elliptic curve with poles just there.
Yeah.
So there's going to be the constant function, of course, 1, and that will be the generator here at the origin, at the vertex. But then the other generators of the Floer complex. So here I have something which is of the 1, and that's actually what's remaining of the fact that the structure sheaf of a closed elliptic curve has H1 of rank 1. But in the usual elliptic curve, this would be H0 and H1 of a trivial vector bundle. But now I have these new generators in this leg because of wrapping. And the claim is these will correspond to things that want to be like powers of something that has a pole at the puncture. Okay. So for example, I'm imagining that I'm placing the puncture at the point -1 because that's the one you can write without coefficients, without subtraction. These would want to be things like 1 over z plus 1 to the k is what xk should correspond to. And now I'm asking, does this ever have a chance of being actually a meromorphic function on this? Well, the answer is no chance. It's not periodic yet. But what if I take its analytic continuation? So if I try this with a single pole, of course I will fail because there's no meromorphic function with a single pole at a single point on an elliptic curve. But I can try anyway. And what I find is this generator is not closed because d of it, okay, so this comes in like that, it comes in with degree 1 here, and I've chosen my coordinate z plus 1. So I look at 1 over z plus 1, and I ask if I go near 0 or near infinity, which are the other two legs.
I'm sorry, just making sure I understand. You're taking that green dot as the input to compute is differential?
Yes, exactly. I'm trying to calculate differential of x1.
And what does the z plus 1 mean?
So z plus 1 is the choice of local coordinate on a pair of pants near -1, near 0, and near infinity. Okay, so that's part of inputs into the model.
Okay.
That I choose for each trivalent vertex local coordinates, and maybe I will choose always these ones. Mirror symmetry, verification by explicit calculation is a weighting, trying to see what you get out of the usual Landau-Ginzburg mirror of a pair of pants.
Okay, so take 1 over z plus 1. And
but for now, I will choose z plus 1. So then I should look at the inverse of that local coordinate because this is x1. If I was looking at x2, I would take that squared. And that's exactly what I'm telling you.
Yeah.
And now, as it goes in, I want to kind of analytically continue this. This has a pole at -1, but it's analytic near 0 and infinity.
Yes.
Therefore, I can calculate the power series expansion near 0 as a power series in Z, that's the coordinate I chose at 0,
Yes.
near infinity as a power series in 1 over Z, the coordinate I chose at infinity.
Yes.
The coefficients look like that. That means this will be allowed to come out in this puncture towards 0 with any degree it wants, basically, but I would count +1 this guy, -1 the one that goes around degree 1, +1 the one that wraps degree 2, and so on. This is an infinite sum.
So are infinite disks, but this expansion tells you how to weight those disks.
Exactly, how to weight all the possible output disks. Okay. But now you can check using some basic combinatorics that the ones actually that come out with positive degrees will never be able to finish anywhere at Y. They will kind of wander around forever and not close up. So the only contributions are in fact this one. And so that's why D of x1 is some multiple of Y. But then you can continue explicitly and do it for x2 and so on. And in fact, you can calculate the coordinate ring of your elliptic curve in a very explicit and painful way if you really want to. Okay. We didn't put this in the paper because it got too painful, but it's with patience or Maple or an undergrad, you can actually calculate explicit bases of functions and recover Weierstrass presentations and all that. I mean, you can do wonderful 19th century algebraic geometry encoded in 21st century symplectic geometry.
Okay, so basically, it's like this local model tells you how many things possible outputs you could get, and then whether they actually realize as this. Or not, depends on the complement.
It depends then on the combinatorics of the picture. That's right. And so you can do all sorts of explicit calculations like that.
Okay, great.
And so like here, for example, you see explicitly that there's no closed generator of a Floer complex with just a single pole. But now if you take the one with an order 2 pole, then the answer is yes, you will be able to, except you need to calculate more about the coefficients, what you will get. And then you will see, well, what you need to correct it with. And actually, you'll get the start of Laurent series expansion of a section of basically of a unique meromorphic function with a pole of order 2 at that point. So basically, this is like a device for calculating in symplectic geometry analytic expansions of analytic functions in various charts, which is kind of a very strange place to end up with in a symplectic paper, but maybe the slogan here is like, this is what mirror symmetry in dimension 1 is about. Actually, it's very, very concrete manipulations of analytic expressions.
So there's no subtlety about like how the 3 prongs of this singular guy are aligned. Like they could be aligned as a corner in the C3, or could they align as something on C2, does it matter?
I think, well, they're intended to be a C3 right now if I want the mirrors to be pairs of pants. I could consider also 4 valent vertices, and then I would have to give you a local coordinate chart on the mirror of that, which would be a 4-punctured P1.
I guess maybe my question is like, on the symplectic side, does it matter how the 3 copies of C glued together at that point?
So in this model, it doesn't yet, because it's just like taking a union of no. I think the answer. Sorry. Well, no and yes. Implicit in this is there's a choice of a reference direction. There's a choice of a reference tangent vector on each copy, and there's a rule for what happens if you rotate those tangent vectors. So there's some kind of trivialization at the vertex happening implicitly, but because anyway, basically there's one model modeled on the coordinate axis in C³ that I care about, and so that's the only one we've looked at.
I see. So you use that local model and you use that as the gluing.
Yes.
But you could, in principle, glue other maybe.
Yes. So now maybe a more grown-up way of saying what I want it to be very concrete and very explicit, but people who are more grown-up would say, well, what's inside that vertex is kind of actually a black hole. It's a black box that will be glued categorically to the Fourier categories of the cylinder of the cylinders that come out of it. Maybe that would be the more honest thing to say. But what I'm doing is I'm drawing very concrete pictures and giving concrete recipes for what is actually at heart a gluing of categories according to a certain rule that kind of inserts a pair of pants in the middle of a bunch of Foucault categories.
Okay, great.
Mm-hmm. Okay.
On the B side, there was a sense in which so say if one looked at the zero brane probes, there was a sense in which of the Riemann surface. There was a sense in which it made sense to consider the quantized Riemann surface.
To consider what?
Instead of considering just Riemann surface to be an ordinary classical Riemann surface,
oh yes, yes.
In which the coordinates on the Riemann surface would not commute.
Right.
And that has to do with higher genus correction of a closed string theory.
Yeah, so I don't know if I have much of a feeling for that. I mean, I understand the statements and it's wonderful, but I'm afraid I'm still stuck in genus 0, so I don't really know how to check what's happening there. Yeah, sorry, I just don't have any smart thoughts about the higher genus story.
Maybe can I have one more question? Okay. So can you, in the part 1 of your talk where you do like a pair of pants decomposition, you said there was some trouble about higher dimension case. What's the trouble precisely?
Oh, so just, well, we don't really know in higher dimensions that this, sorry, where was it? This kind of restriction principle so far only works for actual, one-dimensional cylinders. So I have actually a student working on extending that to more general fibrations over things that have cylindrical necks or products of cylinders and so on. So I think it's possible to extend this, but so far this is only understood in one dimension.
How about the extension to your world of target spaces, which are symmetric products of Riemann surfaces?
Yes, I think it works in symmetric products. That's actually the question I've asked my student to check. So I think the answer is yes. I didn't want to talk about that because so far I have absolutely zero concrete progress to report, but I have 2 students working on 2 different ways of doing decompositions of symmetric products of Riemann surfaces and actually not competing with each other at all. So I'm hoping that at some point there will be some news, but right now it's... But I mean, maybe philosophically, I wanted to say maybe bordered Hegardt Floer pictures, what they draw in those papers about cutting Hegardt diagrams in pieces and so on, kind of essentially says that some kind of algebraic decomposition is possible. I just think the way they say it makes it a bit difficult to really understand what the statement is in the language of Foucault categories. I mean, well, there is a statement that works, but that's not really about decomposing surfaces. I think there's another statement about decomposing surfaces. But that anyway, sorry, that's not yet ready for any kind of discussion. But yes, I believe that there is a similar principle for things like symmetric products, or also for just fibrations over Riemann surfaces and so on. So I'm hoping to have something to report on that at some point.
Okay, any more questions? Okay, if not, let's thank Denis again for a really wonderful talk. Okay. That's a beautiful story altogether.
Thanks. Sorry, it runs really, really long. I need to find a way to make it shorter.
No, this is totally within the usual running times of our seminars, so nothing to
Okay, good. Next, you can invite Nima Arkani Hamed or something like that. We've had him for some marathon sessions here. Okay.
All right.
Thanks very much. Bye.
Bye-bye. Bye, Denis. I hope your daughter's okay.
I think so, probably. But yeah, anyway, thanks. Bye.